Good morning, sir. My name is Bhargavi. I am from EC department, and my topic in DCD is Introduction to Sequential Circuits and their design in Verilog. Introduction to Sequential Circuits and their design in Verilog. Sequential circuits are the system that have memory that can change their outputs based on previous input states. Unlike combinational circuits, their output depend on both current inputs and past states. They are fundamental in digital systems like resistors and state machines. Types of sequential circuits. There are two primary types of sequential circuits, synchronous and asynchronous. Synchronous sequential circuits use clock signals to control state changes. Asynchronous circuits changes state independently of clock signal reacting directly to input changes. Basic components of sequential circuits. Flip-flops are building blocks of most sequential circuits, storing a single bit of data. Latches are similar but level sensitive, meaning they can change state based on input at any time. Together, these components create more complex structure like registers and counters. Flip-flops overview. Flip-flops can be classified into several types including D, T, JK and SR flip-flops. Each type has specific behavior and is suited for different application in digital design. D flip-flops are the most commonly used in synchronous designs, capturing data on a clock edge. State machines. State machines are models of computation representing a system's states and transition. They can be classified into Mealy and Murray types, differing in how outputs are produced. Designing state machines involves defining states, transition, and output logic based on the inputs. Introduction to Verilog. Verilog is a hardware description language used to model electronic systems. It allows designers to describe both the structure and behavior of digital circuits. Verilog is widely used in industry for simulation, synthesis, and verification of designs. Verilog syntax basics. Verilog syntax includes modules which are basic building blocks of any design. Each module can contain inputs, outputs, and internal variables to describe the circuit. Understanding the basic syntax is crucial for writing effective Verilog code. Designing a flip-flop in Verilog. A D flip-flop can be designed in Verilog using the always block and a positive edge clock trigger. The output is updated on the rising edge of the clock based on the input data. This simple design serves a foundation for more complex sequential elements. Designing a counter in Verilog. Counters are commonly sequential circuits that can be implemented using flip-flops in Verilog. The counter state is updated on clock edges, typically incrementing or decrementing based on input. Verilog allows for easy scaling and modification of the counter design for various applications. State machines implementation in Verilog. Implementing a state machine in Verilog involves defining states using parameters or local parameters. The always block is used to describe the state transition based on input signals and current state. Output logic can be defined directly within the state machine or as a separate combinational logic block. Simulation and testing in Verilog. After designing sequential circuit, it is essential to simulate them to verify their functionality. Test benches in Verilog allow for the application of input vectors and observation of outputs. Simulation helps identify issues early in design process before hardware implementation. Conclusion and future directions. Sequential circuits are vital in modern digital design, enabling memory and stateful behavior. Verilog provides a powerful toolset for designing and simulating these complex systems. Future advancement may include more abstractions in design and improved synthesis tools for a sequential circuits. And thank you, sir, for listening my presentation.